Alright, welcome back everybody. As I promised, I would come back with some more examples that we could run through so you get an opportunity to see how exactly you're going to work through these types of problems. So again, this is for solution stoic, and we want to look at these couple of things. We're going to look at first, we got to identify the species that are involved, see what we're actually going to make out of this. We're going to write our balanced net ionic equation, calculate the moles, determine which is limiting, and then convert to our final unit of what we need, whether it be volume or grams or whatever the situation may be. We're going to start off with our first example here, which is silver nitrate is added to 25 milliliters of a 0.5 molar potassium chloride solution until no more precipitate forms. What mass of silver chloride will be formed? Oops, that's supposed to be a question mark at the end, but you guys get where we're going with this. Now, I'm going to go ahead and start off with my reaction. So I have potassium chloride plus silver nitrate, 3, is going to yield silver chloride plus potassium nitrate, KNO3. Now, looking at the relationship we have here between each of these, it's a one-to-one relationship. So, in the end, I'm going to end up worried about my chloride ions. One chloride ion plus silver ion is going to yield me silver chloride, which of course is going to be in solid form according to using my solubility rules. Now, I'm going to go ahead and jump into this and figure out how many moles of my chloride ions do I have available. I can only do this by looking at my potassium chloride because I have a little bit of information for it. So, starting again, I have 25 milliliters, which I'm going to go ahead and change into liters, so 0.025 liters. And the relationship I have is it's 25 milliliters of a 0.5 molar solution. Now, because of the fact that we know that molarity equals moles per liter, I can use this relationship when I go ahead to calculate my moles of my other solutions. So I'm going to go ahead and put my 0.500 moles. Let's go ahead and see if I can't fix that. There we go, 0.500 moles over 1 liter. And we're going to come out with 0.0125 moles of KCl. Now, knowing the relationship that we have between these, I know that for every 1 potassium ion, I'm going to have 1 chloride ion. So, in essence, I can say that I have 0.0125 moles of my chloride ion. Now, I'm going to go ahead and take this same relationship and I'm going to determine how much of my silver chloride I'm going to make. Now, if I have 0.0125, which we moles of chloride ions, I need to understand the relationship between how many chloride ions are there and how many is going to be in my final product, which in this case, luckily, it's also a one-to-one. So for every 1 mole of silver chloride, I have 1 mole of chloride ions. That works out perfectly for us in this case. And since I want to go ahead and convert it directly to grams, I'm going to use the molar mass of silver chloride. 1 mole of silver chloride has a mass of approximately 143.32 grams. Now, make sure that you're checking me on my work just in case I make a mistake. I don't want to have you doing something wrong unnecessarily. So, taking a moment, now we're going to run this through, plug it into our calculator, and come out with a final answer of 1.79 grams of silver chloride produced. This will be our final answer here that we're going to work from. Now, again, check the work as we're going through. I want to make sure that I'm not leaving something in there that might get you going on the wrong path. But this is the basic idea we're going to look at with solution stoic. In this case, we found out the number, we wrote our equation, we wrote out our net ionic equation, we found our moles of our potassium chloride, or of a chloride ion, which is what I have to pay attention to. And then I use that relationship to go into my final product. Now, we're going to go through another couple of examples, and what I want you to understand is when we do this here, it's also going to go hand in hand with what we do in acid-base calculations. So let's look at another example. What volume of 1.25 molar sulfuric acid is needed to dissolve 0.75 grams of aluminum hydroxide, and what is the what is the molarity of the resulting solution of aluminum sulfate? So let's take a look until we have here. Let's write out our equations. First step all the time. So we have aluminum hydroxide, AlOH3, plus sulfuric acid, H2SO4. Now, in the end, this is going to give us a little bit of aluminum sulfate, SO4, 3, plus water. So whenever we see that water is given to us as a product along with some type of metal salt, we know that this is an acid-base reaction. And it follows the same type of rules as we dealt with for our solution stoich. So let's balance this out. We have 2 moles of our aluminum hydroxide to go with 3 moles of our sulfuric and 6 moles of our water. Now, we have our final balanced equation. What are we actually focused on here? Well, you need to pay attention to the aluminum hydroxide, the sulfuric acid that's going to be produced. We need to know what volume. Since I'm looking for the volume, I'm going to keep the whole formula involved here. Now, usually when you see acid-base, we'll be concerned with the water produced, but in this case, we're asked to do something slightly different, so we'll keep moving along. All right, so 0.750 grams of aluminum hydroxide, AlOH3, and I need to somehow relate this to my sulfuric acid. This is what I'm concerned with first and foremost. So, make my table, and find the molar mass to convert it into moles. So 1 mole of aluminum hydroxide, AlOH3, has a mass of 78.01 grams. Okay. Mole ratio is 2 moles of aluminum hydroxide to 3 moles H2SO4. Now, we're going to go back to that same relationship that we talked about before. If I have 1.25 molar, that means in 1.25 moles, 1 liter. Now, the relationship is the same still if I have 1 liter over 125 moles or 1.25 over 1. Okay, I don't want you guys to get confused in that. So, go ahead, plug it into my calculator, and I'm going to come out with 0.0115 liters, or as we would normally work with it, 11.5 milliliters. This is how much of my 1.25 molar solution of sulfuric acid I would need to dissolve this much aluminum hydroxide. Now, there's another step that's actually asked here. Given the fact that we have the 0.75 grams of aluminum hydroxide, what will be the molarity of the resulting solution for aluminum sulfate? So, let's take a look at it. We started off with our 0.75, and I'm just going to go ahead and make another table. But now I'm going to compare the 0.75 grams of aluminum hydroxide to our aluminum sulfate. So I'm just making another table, and I'm just going to include my aluminum sulfate now. So it starts off the same way, 1 mole, AlOH3, 78.01 grams, AlOH3. Oops. Let's adjust that. Let's try to fix that now. 3. Okay. Now the relationship we have between the aluminum sulfate and the aluminum hydroxide is 1 mole of aluminum sulfate to SO43 to 2 moles of aluminum hydroxide, 3. This will give me my number of moles that I need, which is going to come out to approximately, 0.00481. Now, in this we have to assume, since the only volume we have is the volume of the sulfuric acid, we have to use that and assume that that's going to be the only volume that we're dealing with. So, in this case, 0.0115 liters. So, if we take that and divide it out, we get a final answer of here 0.418 molar. Now, we'll continue with other problems like this, and I want you to just take some time and look over the steps that we went through to solve this problem. Bring your questions in class. I have no problem with answering them or trying to walk you through places where you may be confused. Have a good evening, and I look forward to seeing you in class.